activity, we're going to play an online game called Quantum Maze, which was developed by Yao Tang during the 2024 Quantum Games Summer Internship, organised by Quantum Girls. After navigating to the link below, the first step is of course to click play. Once the game loads, if you want to mute the catchy music, then you can click this button at the bottom of the window. And then you'll see the 3 menu options. The instructions options takes us to some useful information about the game, including the controls and some high-level explanations of the maths behind quantum computing. The game then has 2 modes, time attack and speedrun. Today we'll play the speedrun mode and explain the controls as we go. So let's dive right in. In Quantum Maze, your electrons, which are represented by these circular people with coloured hats, are trapped in a maze, and your goal is to help them escape. The only tools available to you are the quantum logic gates, such as this X gate, and/or quantum measurements, which can change the quantum states of the electrons. The aim of the game is then to use the gates and measurements to match the state of each electron, which we can think of as qubits, with the state written on the door. For example, here we need to try and use this X gate to put the electron into the 0 state. Currently, the electron is in the 1 state, which is written in the top left of the screen up here. We can also tell the electron is in the 1 state because it is upside down, indicating that the associated arrow on the Bloch sphere points downwards. So how can we help the electron escape this level? First, by using the Q and E keys, we can select different electrons, but there's only one to choose from here. Notice how the selected electron is highlighted. Once we've selected an electron, we can move it around using the W, A, S, D keys to move up, left, down, and right. Now, by moving the electron over to the X gate here, we can apply the gate to the electron by pressing the space bar, which will flip the state of the electron 180 degrees about the x-axis on the Bloch sphere and change it into the 0 state. This opens the door and allows us to escape, which completes the first level. Also note that by pressing Tab, you can replay the current level, exit to the main menu, or read the instructions. Pressing Tab again closes this menu. In the second level, we can see that the electron is spinning. In this game, a spinning electron indicates that the electron is in a superposition, which we can also see in the top left, where it says the state is 0, minus 1, which is equivalent to an arrow on the Bloch sphere which points to the right. In this level, as we can see on the door, we again need to change our electron into the 0 state to escape. So, as always, we press Q or E to select our electron, then we move it over to one of the logic gates using the W, A, S, and D keys. First, let's apply this H gate, which, as we learnt earlier, will rotate the Bloch sphere 180 degrees around an axis halfway between the X and Z axes. Since the electron occupies an arrow pointing right on the Bloch sphere, this H gate should rotate the arrow so it points down, putting the electron into the 1 state. Applying the H gate by pressing the spacebar, we see indeed that the electron is now in the 1 state, indicated by the state in the top left here, and by the fact that it's pointing upside down. Next, move the electron over to the X gate, and we can flip it into the 0 state, which opens the door and allows us to escape. In the third level, we see our first 2-qubit gate, a swap gate, which swaps the states of 2 qubits. As we know, 2-qubit gates manipulate 2 qubits at a time, so we need one electron on either side to use it. Before that though, notice that we need both electrons in the 0 state to open the doors, but the electron with the red hat is in the 1 state. This is indicated by the state in the top left, where the blue number describes the state of the electron with the blue hat, and the red number describes the state of the electron with the red hat. Now, since we can't access the X gate with the bottom electron, we should first swap the states of the qubits using the swap gate. Now we have the bottom electron in the 0 state and the top electron in the 1 state. Note that the red and blue numbers switched in the state in the top left. From here it is simple. We can use the X gate to flip the top electron, which puts both electrons into the 0 state, opening the doors and allowing us to escape the maze. In the fourth level, we see the controlled X gate for the first time. In fact, here we have two different types of controlled X gates. The first type, with the shaded circle, which is the type we looked at earlier, will apply the X gate to the bottom electron when the top electron is in the 1 state. The second type, with the unshaded circle, will apply the X gate to the top electron when the bottom electron is in the 0 state. So the difference between our gates is that the type with the shaded circle applies the X gate when the electron in the shaded circle is in the 1 state, while the type with the unshaded circle applies the X gate when the electron on the unshaded circle is in the 0 state. Now, notice that both electrons are in the 1 state, so the second gate won't do anything, since the bottom electron's in the 1 state. This means that our only option is to apply the first gate. Since the top electron is in the 1 state, this controlled X gate will apply the X gate to the bottom electron, flipping it into the 0 state. This means that the second gate can now be used to apply the X gate to the top electron, flipping the top electron into the 0 state, which opens the doors and completes this level. Now, in the fifth level, things get a little bit more interesting. First, notice that the electrons are in an interesting superposition of both being 0 and both being 1. This is our first encounter with what is known as an entangled state. Entangled states are special states unique to quantum mechanics, where the physical properties of two particles become linked together. We'll see more about this in the next level. For now, let's try to figure out how to escape the maze. As usual, we need to get both the electrons into the 0 state. And in this level, we've got access to two logic gates, a controlled X gate and a H gate. Let's start by applying the controlled X gate to the electrons, putting the red hat onto the shaded circle and the blue hat onto the X. We can determine what will happen by treating each part of the state one by one. For example, in the first part, where both are in the 0 state, nothing will happen, since the red hat electron on the shaded circle is in the 0 state. However, in the part where the electrons are both 1, the red hat electron is in the 1 state, meaning that the X gate will be applied to the blue hat electron, flipping it into the 0 state. Now we can see that the blue hat qubit is in the 0 state, since it is no longer spinning and is facing the right way up. We can also see this from the state, since both of the blue parts are 0. However, there are still two parts left in the state, which means that the red hat electron is in a superposition, which again we can tell as it is spinning. Specifically, the current state of this electron would be represented by an arrow pointing to the left on the Bloch sphere. So, by applying the H gate, we can rotate the state of the electron to being in the 0 state. This completes the level. In the sixth and final level that we'll go through today, we see the first appearance of a quantum measurement in the game. Notice that just like in the previous level, the electrons are in an interesting superposition of both being 0 and both being 1. This state is also entangled, just like the one from previous levels. Now, the most interesting part about entangled states comes in when we take a measurement of one of the particles in the entangled state. As we know, when we measure a qubit in a superposition, we will randomly find the qubit in either the 0 state or the 1 state. And the same is true when measuring entangled qubits, such as this electron here. However, since the electrons are in a superposition of both 0 and both 1, whatever state we observe the measured qubit to be in, the other qubit will, from that moment on, occupy the same state as well. For example, this time, when we apply the measurement to the left electron, we found it to be in the 0 state, which caused the other qubit to fall into the 0 state as well. However, if we replay the level, and measure the electron again, this time we found it to be in the 1 state, which caused the other qubit to fall into the 1 state as well. The weird part about this behavior is that the actual physical state of the red hat electron, which determines the physical properties of the electron, is changed by taking a measurement of the blue hat electron. To see this, at the start of the level, the red hat electron was spinning, indicating that it was in a superposition. But after measuring the blue hat electron, the red hat electron ends up in either the 0 or 1 state, which is not a superposition. For example, after the last measurement, the red hat electron ended up in the down state. Quantum mechanics tells us that this change in the state of the red hat electron would happen immediately after measuring the blue hat electron, even if the electrons were separated by a massive distance, say light years. This instantaneous change in the state of the red hat electron then implies that information is being transferred between the electrons faster than the speed of light. Einstein called this spooky action at a distance. However, physics tells us that that's not possible. Information cannot travel faster than the speed of light, so we have ourselves a paradox. Long story short, quantum entanglement is very weird, but if you're interested in learning more about it, there are many great YouTube videos describing it. Let's get back to the game though. This level is different to the others because there are 2 doors with different states written on them. To open the middle one, we need to put both electrons into the 1 state, but to open the other one, we need to put both electrons in the 0 state. Since our last measurement collapsed both electrons into the 1 state though, the middle door is already open. So now the goal is to transform both electrons into the 0 state. We can do this pretty easily by first using the top controlled X gate to flip the red hat electron to the 0 state. Then using the bottom controlled X to flip the blue hat into the 0 state. This completes the level and our activity. I hope that this has helped you understand how to use basic 1 and 2 qubit quantum logic gates, which are the building blocks of quantum algorithms, in order to manipulate qubits. Thanks for playing.